Well, hello there and welcome to MoM. This is Axial Video 1. And today we're going to be talking about axial stress and axial deflection. So we start with loading. What does an axial load look like? Well, if you take any object, maybe it's a beam, maybe it's a column, we refer to its longest dimension as its primary axis. So since that's what we refer to as the axis, as the primary axis, that's what we're talking about with axial loading, is any loading that is along the primary axis. In fact, you could have an object that has a force at an angle acting on it. If you wanted to find out what its axial load was, you would take that component that is in the direction of the axial force, or in the direction of the primary axis. We would call that our axial force. Typically, the symbol for an axial force or an axial loading is the symbol P. And the stress, which acts, if we were to take any one of these, let's take this one right here, and take a look at its cross-sectional area. Maybe it's circular, maybe it's square, maybe it's rectangular. If this whole object is in equilibrium, that means every subpart of it is also in equilibrium. So if I draw a free body diagram here, I would get equilibrium. Where you've seen this before is in trusses. The members of a truss are being loaded in the axial, with axial loading. We would have said that this particular member would have been in compression. So when the force is perpendicular to the area, we call that normal to the area. The stress is a normal stress. So now we're talking stress. It's normal stress. It is perpendicular to the cross-sectional area. When we have, in mechanics of materials, a stress perpendicular to a cross-sectional area, we use the lowercase Greek letter sigma. And the equation is very simple for axial stress. It is simply the force divided by the area. So this is axial loading. This is axial stress. What would the units be? Well, let's see. If our stress was in, or if our force was in newtons and our area was in square meters, we would have units of pascals. Or if our force was in pounds and our area was in square inches, we would have units of PSI. Typically that symbol there, the bracket around the equal sign, is representative of the units. All right, so let's press pause and flip the paper here. So mechanics of materials, taken at some universities, is called deformable body mechanics. Now what deformable means is changes shape. So in statics, you often heard the objects being referred to as rigid objects. We were assuming that when we applied a force, there was no change of shape. In mechanics of materials, we take one step into the real world where when you apply a force, you get a change of shape. So the next thing we're going to look at is axial deflection. So let's take an object, let's connect it rigidly to a wall, so this wall can't move, and we'll apply a force on the object, and what happens is the object actually gets, in this case, longer. In fact, due to conservation of mass, it not only gets longer, but if to keep its same mass, it's going to have to get skinnier. But for now, let's just deal with the longer. We call this amount it got longer the deflection. And we use the lowercase Greek symbol delta. If our object had an original length of L, a cross-sectional area of A, had a force applied P, then the equation for delta is P L over A E. Now, original length, force, area, what's this? E. You may have come across this in your statics class. It is called the modulus of elasticity. Also known as Young's modulus, named after a dead guy. It is material dependent. So steel has a different modulus of elasticity than rubber, than plastic, and that should make sense to us. That not only does the delta, does the deformation or deflection depend on force and length and area, but also on what is this material? What is it made out of? So there we go. There we have it. We have axial deflection. Let's run through the units real quickly. I do expect all my students in engineering classes to use a railroad track method. Let's do this in pounds, in English. So force would be in pounds. Length would be in inches. Area would be in inches squared. And it turns out that the units of modulus of elasticity are PSI, or pounds per inch squared. P, L, A, E. Now we cross things out, cross out the pounds, cross out the inches squared, and we get a deflection in inches. We would expect that the increase in length would be in inches. This equation works for increases when something is in tension. Also works for decreases when something is in compression. So there we have axial deflection. And lastly, in this video, we're going to talk about axial strain. So strain is likely to be a new concept for you. We talked about something having a load applied to it. Again, either tension or compression. And then that thing getting longer. If we call this the original length and we call this the final length, if you applied a load to something that was free to move in both directions, it would increase by a length of delta. So we would actually see delta over 2 on both ends. It would make sense here then that the final length would be equal to the original length plus delta. This increase in length, or delta, is kind of like an absolute term. You had a 10-foot long beam or object, and it got a 1/10 of an inch longer, and now we know that it's a 1/10 of an inch longer. And that's useful to an extent, but what we like to do is to normalize that increase in length. And basically what we do there is we take delta and divide it by the original length. And now it doesn't matter whether you had an 8-foot long to start with or a 10-foot long to start with. The change in length by being divided by its original length is somewhat normalized. We have a name for this change in length over original length. It's called strain. It's got a symbol of epsilon, and it's the increase or decrease in length divided by original length. Now, if I were to ask you what the units are, you might say, well, if we started with inches and we increased in length by inches, the units would be unitless. But while you would be right, they are in a sense unitless, we don't call them unitless. We say that the units of strain are inches per inch. In other words, for each inch of the original beam, the increase or decrease in length was so many inches. So a typical value for strain might be 0.001. That means that if you started with 1 inch of an object and it had a strain of 0.001, after it, this is a little bit exaggerated, after it got increased, not to scale, it would be 1.001 inches. Strain can also be negative if, in fact, you are compressing rather than tensioning. Now you could say, well, what if I had a 120-inch long piece? Well, then I would, for every inch, get 0.001 inches longer, multiply that times 120, and I would have my new delta. So anyhow, it's a thing. We call it strain. It has units of length per length. It has an equation of delta divided by original length. You'll see that axial strain is something that is important. See you in the next video.